Good afternoon. So let's get started. A few things I want to bring your attention to are the announcements, okay? Today we're going to cover section 7.3 in the book, but I'm going to do some additional stuff, okay? So it'll be 7.3 plus some information that I'm going to give out in the PowerPoints. Thursday, okay, we're going to be doing activity 3. So activity 2 was the quiz that we had. They're not all in-class activities, okay? Now I'm going to tell you this for a reason. I know that spring break is coming up, and there's a temptation sometimes to start a little early. Resist that temptation, because this particular activity is going to be pretty much like the foundation that the rest of this entire semester is based on. This would be a bad activity in this. As far as things that are due, you know, homework 5 is due, okay, on this Friday. And activity 3, which we're going to do on Thursday, will be due the Wednesday of the day that we come back. Okay, the week that we come back. So the week we come back, that Wednesday, March 22nd. I'm going to ask you to turn in a hard copy. Remember about the SI, okay? So just be aware that you can take advantage of that. All right. Oh, one last thing I wanted to mention. So someone asked about the final. And so I feel like I'd be remiss if I didn't give you a word of warning, which is you really have to be there for the final, and there are no makeups for the final. And I tell you this because this is about the time when people start to make their travel plans to go home. And I actually had a situation in business stats last semester where a student ended up failing because she made her travel plans and didn't take into account the final exam and opted to go home rather than take the final. And the final's worth 20% of your grade. And so, unfortunately, that's not on me. That's the department. I try to be as flexible as possible, and they have activities and other obligations. But finals is really reserved. There should be nothing going on in final, and really no excuse. So please, if you're not sure the final is, see this little icon that says nobody ever reads me? Click on that, check out the final exam. Make sure that you know that before you finalize your travel plans, okay? After is just too late. Questions?
Yeah, is it going to be like a written exam or online?
It's going to be online.
Okay.
So it's really cool because as soon as you take it, you know what your final exam grade is, and you also know your grade for the class. So I don't know if that's good or bad, but you know, instant information, okay? So what I'd like to do today is I'd like you to go ahead and open up these 2 data files if you haven't already. So these are data files we've used in the past. You know, a good rule of thumb is whenever we use a data set, save it. And that way you don't have to reload it each time. You can just go to My Data and bring it up. Great. So go ahead and open up those 2 if you haven't. And what we want to do today is we want to talk about, so you notice that being normal is a really kind of cool thing. You can get a lot from that. We're going to see that you can get a lot more. The question is, though, how do you know that the data you're looking at is normally distributed? Now you might say, well, it's really easy, okay? I mean, you gave us all of these criteria, right? It's bell-shaped, you know, it's symmetric, it obeys the empirical law. Here's the problem. That never happens with real-life data, right? So we said if all these things are true, we have a normal distribution, but with real-life data, none of those things are true, right? We rarely have a population, okay? The histogram is always chopped up. It's never a nice curve, okay? So the question is, you know, with real-life data, how do we know if it comes from a normal distribution? And so what I want to do is I want to do a simulation. So I want to kind of convince you of a few things that you might not be aware of. So if you go into StatCrunch, what we're going to do is we're going to generate random variables from 2 different distributions. One's going to be a normal distribution, and one's going to be a distribution that looks like a normal distribution, but it's not. So first we're going to generate 500 values of a random variable that comes from the standard normal, right? And so you guys know how to do this now. You go to Data, Simulate Normal. So I'm going to simulate data from a normal distribution. And when you do that, this little dialog box appears. And so we're going to enter 500 here. This is going to be the number of random variables values we want to create. And then of course we have to tell StatCrunch, well, what normal distribution do you want, right? So what's the mean and the standard deviation for a standard normal? Something you should know. 0, 1, right? Okay. So go ahead and enter 0, 1 there. And you can just hit compute. So I'm going to do that along with you, okay? Here. Stat crunch. And so I'm going to say data, simulate, and go down to normal. And then I'm going to tell it I want 500 values. Okay. And the mean is 0 and the standard deviation is 1. And we go ahead and hit compute. And so you should have now one long column all full of numbers, right? How's that going? Okay. Well, that's okay. You just did it on top. And that's okay. That's okay. And you can open up a blank thing if you want, or you can do it in a data set that we've already done. And you can look up with someone else if you want. Okay, you good? Okay. All right. Good. We already got it. You want to walk through? Sure. Okay. Now what we're going to do is we're going to simulate. So any questions on this? Everyone's getting that to come up and work? Okay. So now what we're going to do is we're going to simulate 500 values of a random variable from a different distribution. This is called a t-distribution. And we haven't talked about this yet, but we're going to. And so it'll be exactly the same steps. Data, simulate, and now you're going to go down and you're going to hit t. And do exactly the same thing, except when you get to this box, the parameter that you have to specify for a t-distribution is not a mean or a standard deviation. It's something called degrees of freedom. We're going to talk about that later. But for right now, just put 6 in this box. Okay. We'll just treat this like a black box. So here I'll work alongside. So the exact same steps: data, simulate, and now go down to t. Okay. And why it's called t, there's not really a good reason. There's historical things about it. Okay. So again, I want to generate 500 values. And all I'm going to do for the degree of freedom is just put in 6, okay? And we'll go ahead and do that. So now we have 500 values from this other distribution. Everyone's good on the t? All right, good. Okay. All right. Now let's go ahead and make a stacked histogram. Let's plot both of those together, okay? So let's go up to graph and histogram, right? So if you remember what we did before, when we make a stacked histogram, we're going to go ahead and we're just going to choose our variable, right? And then we're going to do relative frequency, okay? You can click the mean and the median. You don't have to. The main thing is this, though, right? We want to stack the 2 plots. So I'm going to say 2 here. That means we'll have 2 rows of plots, right? And I'm going to plot them on the same x-axis, all right? So let's try that. Graph, histogram. I'm just going to select both. And then I'm going to say relative frequency. And you can do the mean and the median. It doesn't matter. Okay. And I'm going to do 2 rows per page. Same x-axis. And I'm just going to fill this in. I'm just going to say, variable relative frequency. And then we could say comparison normal versus t-distribution. Okay? I just want to compare those two. And when you do that, you should see a plot that kind of stretch this out so the aspect ratio is pretty good. You should see a plot that kind of looks like that. Okay. Your plot will be a little different, right? Because that's the whole idea behind a random sample. Everyone's going to be different. And notice those two plots, they both look normal, don't they? If you want to get a little better view, you can kind of stretch it out a little bit. Right now it's kind of scrunched up. So here's kind of the moral of the story, is that the normal distribution is not the only symmetric bell-shaped distribution, okay? So we can't go purely on looks, all right? You know, and yours probably looks, this is a little asymmetric for a t-distribution. Yours probably looks a little more symmetric, right? So we can't go just based on the looks alone. So this is kind of the moral of the so get stuck sometimes. There we go. Okay. So here's kind of the thing to bear in mind is even if you had something from a normal distribution, this is just a partidissima normal distribution. Notice it doesn't obey any of those three properties, right? Okay. It isn't a curve because it's from data. It isn't perfectly symmetric, right? And if you were to do some really careful calculations, you'd see that the empirical law is not exactly obeyed. So none of these three things that we say the normal distribution obeys for a population or obeys for a data set, right? How do we know for sure if that data comes from a normal distribution? And what we're going to do is we're going to test it. So the idea is that we're going to first do what we call visual tests, okay? We're going to perform a lot of different tests this semester. And every test we do starts with a visual test. In other words, we're plotting this data not just to describe what it looks like. If that's all we did, it'd be kind of boring. We're trying to answer a question, right? So this plot is kind of testing this question. And so we always start off with these kind of visual tests, okay? Now what we want to understand is there's two ways to plot data from a normal distribution. The first is a histogram. And the idea is that the histogram weeds out things that obviously are not normal. So for example, if you have a really large data set, right, and you plot the histogram, and it looks maybe like the Major League Baseball salary, right? That histogram alone tells us that it's not normal. There's no reason to do any more tests, okay? But we're going to see that sometimes data sets can still pass that histogram test. In fact, the t-distribution just did. We looked at that, it looked normal, but we know for a fact that it's not. It's not from the normal distribution. So what we're going to do now is we're going to do a second type of plot called a QQ plot. We're going to see what that is in a second. And that's going to be a second way that we can kind of weed out, okay, things that aren't ruled out by the histogram. So here's the idea behind a QQ plot. It's basically a plot just like the histogram, nothing special. But what happens is, when you have data that's normal, it turns out that the points fall on a line, okay? So StatCrunch, when you do this, it naturally puts in this line, and you can see that this is actually from data from a normal distribution. You can see that the points fall very, very close to that line, okay? And so that's what the data is going to look like when it's normal. When it's not, what's going to happen is the points are going to go away from the line at some point. You're going to have really strong deviations, right? So here's the line, and you can see that there's really strong systematic deviations, okay? And so we're going to use this also as a way of kind of telling if something's from a normal distribution or not. So let's kind of practice doing this and see what it's like. But before we do this, I want to show you one last thing, which is we know that skew causes something not to look normal, right? And so these are the different types of QQ plots you have for different types of shapes. So if, for example, I have a left skew distribution, you can see that the points don't fall on the line, and there's kind of like a curve, kind of form like a curve above the line, right? If I'm normal, of course, the points are going to fall pretty much on the line. Nothing's perfect, okay. But the idea is that if we have any doubt, if we fall in a region where there's any doubt, then we're going to do another type of test. We're going to do a really strong test to determine for sure. And finally, if we're right skewed, okay, the same sort of thing happens. The points don't fall on the line, and they kind of form an arc below. Okay. So any sort of deviations isn't going to mean it's not normal. So let's go ahead and go to the data set we had for the cars, okay? So we had the Cadillac data set. And you remember in this data set, we were looking at the price of Saabs and Cadillacs, right? We kind of took the original data set and kind of winnowed it down. Bless you. Okay, there we go. And so let's make a histogram first, okay? Let's make a histogram of the price for the Cadillacs and the Saabs. So we'll do histogram, price. I'm going to group by make, do relative frequency, right? And then I'm going to make 2 rows per page and put them on the same x-axis, okay? And we got something like this. And we did this plot before. So you look at those 2 plots. Which one is definitely not normal?
Cadillac.
Definitely. So there's really no reason to test any further, right? We know for a fact that's not going to be normal. But what about Saab? Saab looks pretty symmetric, doesn't it? Okay. So let's try to make QQ plots of these and see what these look like. So what should we expect? What do we predict? We predict that the QQ plot for the Cadillac should not fall on those lines, right? There should be some really, deviations from that line. And if the Saab really is normal, those points should kind of fall on that line, right? So let's go ahead and try it. So now we'll go to graph, QQ plot. The QQ stands for quartile to quartile. And what's actually happening, just tell you very, very briefly. What it's doing is it's taking each data point, it's figuring out the percentile, and it's computing the z-score for that percentile. So it's plotting the data value versus the expected z-score if it was normal. And when it turns out that it's normal, the points fall on a nice line. Okay. So we're going to do price and group by make. Okay. And we're going to have 2 rows per page, and we don't have to worry about the same x-axis, okay? And go ahead and hit compute. And we see that the QQ plot kind of confirms our suspicions, right? So the Cadillac, we said it wasn't normal, and sure enough, the QQ plot, the points are way off the line. The Saab we thought was normal. And we're seeing a little bit of deviation, but notice that it's not systematic. The points are kind of coming back to the line.
The line is there for us to understand the plot somehow?
That would be what you would see if it was perfectly normal.
Okay.
The points would lie exactly on that line. So that's kind of like the standard you're judging. And how much those points deviate from that line is telling you how far it deviates from a normal distribution. Now you might say, well, I see some deviation here, and that's true. And you might say, well, how do I know how much deviation? Well, when we're in doubt, we're going to do more tests. It turns out there's a really good test that will definitively answer that question. Okay? But this kind of shows you, so again, this is kind of like a weed out thing, okay? And so one of the ways that we're going to think about these tests, we're going to see that it's very much like a criminal trial, okay? I mean, this is exactly what it's like. The plots are kind of like the grand jury. Okay? So this is evidence as to whether or not we're going to test it further. We're going to put it on trial. So notice that this first plot, this is evidence. This is like a case where we don't even bother going to trial. We're judge, jury, and executioner. We already know this is not normal, right? This, we're not sure about. There's a little bit of deviation, okay? So there might be enough evidence to bring this to trial, okay? Or actually test it further. So now it turns out that actually something else can go wrong too. You can have skew. But it doesn't have quite the right shape. So in other words, this is the normal distribution in the middle. But it's possible you can have something that's symmetric, but it's too thin to be a normal. Or conversely, you can have something where the tails are too thick. And if you go back and look at that T distribution, the one that we did in the beginning, you'll see the tails are too thick. It's thicker than normal. Okay. Now, what happens to the QQ plot when that happens? Notice that it's very hard to tell from the histogram. It's not so easy to tell from the histogram if it's normal or not, because they're all symmetric, okay? And they all have kind of a bell-like shape. But when you make the QQ plot, sometimes you can distinguish, okay? So this is when it's actually normal. The points are kind of on the line, right? When it's too thin, you see pretty strong deviation, right? And when it's too wide, you see a lot of deviation also. So this is something else that can go wrong. So even if it looks nice and bell-shaped, we still want to test it. So let me just kind of show you an example. Let's go to that S&P 500 data set we had. So that was the data set where we were looking at the S&P 500 returns, right? And let's make a histogram first. Okay. So we had all this data, and remember what we were looking at is we were looking at the log returns. This is what we were looking at before, right? That's what defined volatility, right? Let's go ahead and make a histogram of just the log returned. So I'm going to do graph, histogram, and I'm just going to do log return, okay? And you should get a plot that looks like that. Now when you look at that plot, what do you think? Is that normal? Does that look like it came from a normal distribution? It is too thin, right? In other words, the tails are really small, there's too much mass in the middle. If you were really to take that bell shape literally, like we do, that would be like a really thin bell, right? So let's go ahead and make the QQ plot for this and convince ourselves this isn't a figment of our crazed imagination, okay? But notice that here, basically what we're saying is that the tails are too thin, right? This thing has too much mass in the center. Let's just convince ourselves that's true though. So if we go to the QQ plot now, and we plot the log return, now we can see unambiguously that that's not normal, right? The points are way off the line, so there's no way you can interpret that as normal. So again, we're kind of like judge, jury, and executioner at this point. We know for sure that this is not normal, okay? Any questions about QQ plots, how we make them, problems that you're having? So here's something fun. Let's go back to the normal and the t-distribution, right? The t-distribution we couldn't tell by looking. Can we tell from a QQ plot? We said it's a little too thick, right? So let's go back to the, let's see, where is it? So back here where you did the t-distribution, the normal, let's make QQ plots now for this. Okay. So we're going to do QQ, whoops. I'm going to choose both of them. Okay. And I'll put 2 per page. All right. And we go ahead and compute that. Now, I might not be sure about this, but am I sure about the normality from this plot? Sure. These points aren't anywhere near the line, okay? Let me ask you a question. Who has a QQ plot that does look like the thing is still normal? Okay. Sometimes it happens, actually. Yeah, right. So sometimes you can still pass that. So he has one there, and it's probably not that unusual. You have one.
Mine are pretty close.
Yeah.
So is mine.
And notice that there are, yours is, okay, so yours has enough deviation, probably, yeah. So it's kind of a crapshoot, right? So some of those we might have to test a little bit further. Okay, yours is really close, yeah, yours is really close. Okay. Nope, yours is pretty far away. So even with these distributions that are kind of thick-tailed and thin-tailed, you might take a sample that still makes it look like it's normal, right? It's kind of like the luck of the draw. Yours is questionable. In fact, it almost looks less normal than this, you know, okay? So what we're gonna do after we come back from the break is we're gonna look at a method to kind of definitively answer this question. If for some of you that had that kind of like weird sort of situation, we're gonna have a test that will answer that definitively. So let's go ahead, take a break. We'll come back and we'll do the acid tests, so to speak. Do we have the roll, by the way? Everybody that always happens that way. Like somehow it sneaks around. And everybody else got it?
It always makes its way around the back.
Weird.
also your academic study plan, you should be updating it. Most university success, you look at plan it all out. You know, you have to take it. So usually it's a freshman class. Oh, you get credit for it. I thought it was a really BS class. You don't learn anything. You just said, you talked about managing stress, sleeping and right amount of times. You know. Well, it's supposed to be like an easy A. It's only, I think it's only one credit. So it usually doesn't fill up, take any longer to take that class. It's only one credit, everything threes. Some things are fours. 3 hours. A week?
Are we ready? Okay.
Unless they're way more.
Okay. So now we want to have this thing called a hypothesis test. Okay, so this is where we're going to really test whether or not it's normal. Now, those ones that were really bad, we could test if they were normal, but there's really not any need to. Okay, so you could say, well, you know, those things definitely had evidence that they weren't normal, and that's true. But here's kind of the idea behind a hypothesis test. What we're doing now is we're getting into the last phase of the class, which is inference. And inference is when we generalize. So we take you know, a sample from a population and we try to generalize to the whole population. And you hear about this every day in the news, right? People take polls like what percentage of people think Trump should be thrown from a train or whatever, right? There's all these polls now. And so how do they do that? Well, they only take 1,000 or so people, 1,000, 2,000 people in that sample. They generalize to over 100 million, okay? So this is the idea behind an inference, okay? And by the way, we do this all the time. In fact, probably like 95% of what we know is all through inference, right? I mean, there are very few things that we know absolutely, positively are true. Like I went to Portland not long ago, okay? I go out on the first day it's raining. I go out on the second day it's raining. I go out on the third day it's raining. What do I conclude? It rains a heck of a lot, right? Even though I was only there 3 days. So sometimes, you know, it's valid and good, but sometimes we make generalizations that are bad too, right? So in our case, what we're going to do, here's kind of the hypothesis that we're interested in looking at. We have data from a sample, and we want to generalize to the population. We want to say, first of all, I think that data came from a normal distribution. In other words, that was the parent population. And the other possibility is that it didn't. We always have these two competing and opposite hypotheses, okay? Now, what I want to do first is just go through the mechanics of how we do a test for normality. And then we'll talk about what we're actually doing, okay? So first, we're gonna run a hypothesis test for normality. We have these two hypotheses. Don't worry about the names right now. They're called the null and the alternative. Don't get caught up in that. But basically, these are the two possibilities, right? Either the data comes from a normal distribution or it doesn't, all right? And what we're going to do is we're going to run a hypothesis test that was developed by two guys. They're called Shapiro and Wilkes, okay? There's a lot of tests for this, but theirs is probably the best. We're going to use StatCrunch. And so the way we're going to get to this test is we're going to go to Stat. And when you click on the Stat label, you'll see another little list pop up. Choose goodness of fit, and finally normality, okay? So you're going to go to goodness of fit, and you're going to choose a normality test. Okay. And goodness of fit, what it's doing is it's testing to see if the data fits a normal distribution. That's what that means. Then we're going to choose the variable that we want to test, and we're going to see if the output gives us what we call a p-value. So let's go ahead and do this. Which of the data sets do you want to work with? Which ones do you want to test? You got a couple now.
The normal ones.
Okay, so you want to do the normal and the t. So let's go ahead and do the normal and the t. So we go back to our normal and our t. Okay. In fact, we're already here. And I'm just going to close these now. Well, minimize them maybe. And so I'm going to go to stat, goodness of fit, and do the normality test, not the chi-squared test, okay? And I'm going to click both of them. And notice that you can do the QQ plot and the histogram at the same time, okay? But we usually do those before we run a hypothesis test, okay? And I'm just going to go ahead and click compute. And here's what I'm going to focus on. I'm going to focus on this thing called a p-value. And so we're going to make a rule for that we're going to explain later on right now. Here's what the rule is going to be. So for our hypothesis test on normality, our rule is going to be this. When the p-value is less than 0.05, we're going to conclude that the data did not come from a normal distribution. Okay. When the p-value is greater than or equal to 0.05, we're not going to say that it does come from a normal distribution. We're going to say something a little more nuanced, okay? So when the p-value is either greater than or equal to 0.05, what we're going to say is that there's not enough evidence to say that it's not from a normal distribution, okay? Okay. And we're going to talk about why we have that wording in a minute, okay? If we look at our results right here, what do we see? Well, for the t distribution, does anyone have a p-value that's greater than 0.05? One person? Anyone else? Okay. Two? Okay. Anyone else? Show of hands.
0.05, yes.
So it has to be less than 0.05. I'm sorry, greater than.
Yes.
So for the t distribution, let me know if your p-value is greater than or equal to 0.05. So yours? Okay, yours. Anybody else? Yours? Okay. So it happens, right? And those were the ones where your QQ plot looked really linear, right? Is that right? I know yours did, right? Your QQ plot looked really linear, right? For the t distribution?
Yeah.
Okay, and yours also?
I already closed it out.
Okay, all right. But my guess is it did, okay? So those were, so sometimes you can still get past a hypothesis test, okay? But notice that most of the time it didn't, for the majority of us. And how many people in the room? 1, 2, 3, 4, 5, 6. So let's say 15 people are doing computing, okay? So 3 out of 15 ended up getting through the hypothesis test, even though it wasn't. And we're going to discuss why that is, okay? But most of you would have got a p-value less than. So notice that in my case, this p-value, right, is less than 0.05. So I would say for this t distribution, it didn't come from a normal distribution. The other one, I would say there's not enough evidence to say that it did, okay? Let's do another one. What's another one that maybe we want to do? What about the Cadillac and Saab? Let's go ahead and try that. Okay, let's make a prediction. What should we see for the Cadillac and the Saab, okay? So for the Cadillac and the Saab, should the p-value for the Cadillac be less than 0.05?
Yes.
We totally expect that, right? Because when it's less than 0.05, it's not normal, and we totally think that. The Saab we're not sure about. I would probably say no, okay? I'm gonna make a prediction no. And let's go ahead and check it and see. So stat, goodness of fit, normality, price, and I'm gonna group by make, okay? I want to compute them both at the same time. And sure enough, you can see when you look at it, the Cadillac's less than 0.05, we would conclude it's not normal. Well, we already knew that, right, from the plot in the QQ, okay? But that totally seals the deal. For the Saab, okay, notice the p-value is above 0.05. So we're not going to conclude that it's not normal. We're going to believe that it is from a normal distribution, okay? All right, good. So what I want to do is I want to talk a little bit about for some reason Windows keeps cutting out today. I don't know why. So click this really quick. So we're going to be talking about hypothesis tests a lot. Hypothesis test is a very general thing. It actually goes outside statistics. It's part of philosophy. Epistemology to be exact, okay? Hypothesis is just a belief. We have lots of beliefs. Beliefs about whether or not aliens exist, whether or not you're going to get a good job, right? We have all sorts of beliefs, okay? Again, the sort of beliefs we're going to test in statistics, we're very limited to what we can talk about. The only beliefs we can test are beliefs about a distribution. We take a data set and we say, I'm going to test whether or not it's from a normal distribution. Or I'm going to say, it's from a normal distribution, I'm going to test to see if the mean is something. So we're very limited in the sort of beliefs we can talk about, okay? And the two beliefs we're always going to set up are these two things called the alternative and the null. So the null hypothesis is what we believe if we have no data, okay? It's what we start off believing. The alternative, it used to actually be called the research hypothesis. That's a really good name for it. It's the thing that we're trying to prove, okay? That we think is true, and we want to see if the data is going to prove that for us. So when we're doing a test for normality, it turns out that the null hypothesis is that's from a normal distribution, which is kind of strange. You would think that normality is something you have to prove. But for this particular test, this is a null hypothesis. And it turns out the alternative is just the opposite. These are always opposites. The data is not from a normal distribution. Now, how does a hypothesis test work? Okay, we start off with these two different hypotheses, okay? And the idea is, the way we choose between them is we think of the data as evidence. So I'm going to keep going back to this analogy between a statistical hypothesis test and a criminal trial because they're almost identical, okay? You start off, for example, in a criminal trial, the null hypothesis is that you're innocent, right? And then we're going to present evidence, okay? So we're going to start off believing that the null is true, and we're going to think of the data as evidence in favor of the alternative. And the way we're going to decide at the end of the day which one to choose is we're going to ask ourselves, is the data overwhelmingly against the null hypothesis? And if it is, then we're going to choose the alternative. Okay. So let me kind of give you an example, okay, with a criminal trial. So suppose I'm accused of murdering my next door neighbor, Bob, okay? I didn't, I swear. Look at this thing.
He did it.
What's that?
I know he said he did it.
I'm not a crook. So let's look at the two hypotheses, right? First thing you do is you go into court, and the thing that we believe in the beginning, okay, the hypothesis we start off believing in the absence of any evidence against me, the null is that I'm innocent, right? So that's the defense position, okay? And the alternative, the thing that we're trying to prove in a court of law is that I'm guilty. That's the prosecutor, okay? And that's the very first thing when you go before a judge, right? He asks you, how do you plead? So these two sides, you know, they state their hypotheses, right? So what happens next? Well, they present evidence, okay? So maybe, for example, in the beginning there's no evidence, but then someone says, well, you know, I saw him arguing with Bob. He had a really heated argument, right? And then maybe they find my fingerprints over at Bob's place. And then maybe it comes out that my wife was cheating with Bob, okay? So now I have motive, right? And then maybe they find the murder weapon in my house. So this is the evidence against me, okay? And so in statistics, you know, we start off, the evidence is a plot. We plot something, it doesn't quite look normal, right? That's kind of like the grand jury. Then we're going to take it a little bit further, okay? So what we have to decide is there enough evidence, okay? So here's kind of how it works, okay? So here's the evidence against me. And this last column is really important. So this is the probability that the null is true, that I'm not guilty, based on the evidence, right? So when we start off, what is the probability that I'm innocent at the very beginning of the trial?
When there's no evidence?
What's the percentage, the probability I'm innocent?
So I guess it would be.
Is there really a probability, or is
I don't know.
is that a trick question?
Will the jury, if they had to decide, right, probability I'm innocent or guilty, without any evidence, what would they
50-50.
decide?
It's 100.
It would be 100% because they have no evidence.
It's going to be 100%, right? Because there's no evidence against me. So right now, you know, everything's in my favor before any evidence, right? They have to decide that I'm innocent. If the prosecutor comes in and says, hey, guys, I don't have any evidence, I'm going to walk free. 100% of the time, right? Now they hear that, you know, Bob threatened me, okay? So in the jury's mind, the probability that the null is true, that I'm innocent, given this data now, goes down a little bit, right? And when they find out that, you know, my fingerprints are at the crime scene, it's now 50%, right? And then they find out that my wife's cheating with Bob, it goes down further, right? And then they find the murder weapon, and now it's really low, okay? Now it's possible that I'm innocent, right? I mean, people can be framed. In fact, maybe my wife is tired of both of us, and she offs Bob, and she frames me. Right? Could happen. I mean, and people all the time get stuck in incredibly unfortunate circumstances. They just happen to be at the wrong place at the wrong time and look like the wrong dude, okay? But what happens is we say, okay, when the probability that I could be innocent, given all the evidence, is so low, we have to decide at some point, right, that I'm guilty. We have to throw away the null that I'm innocent, and we have to say, I believe that the person's guilty, okay? So that's kind of what's going on in a hypothesis test, okay? Sometimes people call this, they call this thing the p-value that we're going to talk about, kind of like the level of gullibility. How much evidence are you willing to accept before you finally say, I don't think the null is true anymore? The evidence is overwhelmingly against it. So this is what we call p-value. This is probably the most misunderstood concept in statistics. So the p-value is the probability that the null could be true given all of the evidence against it. Okay? And so when the p-value is too low, okay, like in this criminal trial, okay, it's so unlikely that all that evidence could be true and I'm still innocent, right? Then we have to reject the null hypothesis. We have to say that person's not innocent. They might be, but it's just too low, right? And generally we make this threshold at 5%. When the probability that all that evidence against the null could happen and the null could still be true is less than 5%, then we say, okay, I don't believe the null anymore. I'm going to accept the alternative, okay? And so at this point right here, you know, we say, okay, you know, we don't believe the null anymore. We don't believe that he's innocent, right? Even though I could be, it's just too unlikely that all that stuff could occur and I could still be innocent, right? That's the idea behind a p-value. So just to kind of review, here's what's going on, okay? When the p-value is less than 5%, we reject the null, we accept the alternative. The null might be true. It might be that I'm innocent. But there's just too much evidence against me. A reasonable person would decide it's too unlikely, right? Okay. So this is a case where a person's found guilty. Now they may be innocent, but the evidence is overwhelmingly against them, okay? When the p-value is above 0.5, we fail to reject the null. We don't say that it's true. If you think about a criminal trial, right? The jury never comes back and says the person's innocent, do they? They definitely say they're guilty, but they never say they're innocent. They say there's not enough evidence to prove that they're guilty, right? All the time we see people on trial. We know for a fact they're guilty, right? They get off. The jury doesn't say they're innocent. They just say there wasn't enough evidence to convict them, right? That's the idea. Okay. Which one's more important? Well, it depends. Okay. In some applications, like if you're doing homeland security, for example, all right, you don't want to let anyone who's guilty through. That can have really catastrophic consequences. Okay. So you'd be really worried about making this mistake. Oops, I'm sorry. Making this mistake right here. A person's found not guilty. A person, say, is not considered a terrorist when they really are, okay? In this example here, it depends. You know, if you're really liberal, what are you gonna say? You're gonna say, I don't want to convict an innocent person, right? If you're really conservative, you might say, well, I don't want to let guilty people roam around on my streets free, okay? So it kind of depends upon what your objective is, all right? Okay, we're going to come back to this a lot more, but just to give you a little foretaste about hypothesis tests. So that's all for today. Do you have any questions? We're all good? Okay, thanks. I'll see you on Thursday.